formula mass, which is what? What is formula mass? You don't know. Okay. So formula mass, it's the what?
Sum of the average.
So formula mass is the sum of the average of the atomic masses, right? So you can figure out your formula mass when you have aluminum oxide, right? You can figure out the formula mass of Al2O3 from the averages of the atomic masses of aluminum and oxygen, right? You could also do that with CH4. You can figure out your formula mass from the average atomic masses of the carbon and the hydrogen, right? So formula mass is kind of the big picture. It's like the big idea. All sums of the average of the atomic masses are going to be formula masses. Does that make sense? Well, molecular mass is, I guess, more specifically associated with molecular / covalent compounds. Does that make sense? You know the other term for covalent is molecular compounds, so that's why molecular mass is more specific. Dr. Franco wants you to think of it as more specific to covalent compounds or molecular compounds, because another word for molecular compounds is covalent. Does that make sense? So I guess molecular mass and formula mass are the same thing when you talk about covalent compounds, but they're not. You can't call the formula mass of an ionic compound molecular mass, technically. Does that make sense? Usually it doesn't get as specific and higher. Like, I apologize in advance if I say molecular mass when I should say formula mass, because I was never taught that specifically before, because it's kind of it can be seen as a technicality, because it's a very technical concept. So I apologize in advance when I should say formula, I say molecular. Just remember on the test, please don't let my slip-ups confuse you. On the test, I guess what Dr. Franco expects is that when you say molecular mass, it's specific for covalent compounds, while formula mass applies to both ionic and covalent. Does that make sense? But again, I'll double check with her to make sure that that's the right distinction. And that way we're consistent with what Dr. Franco expects from you. Make sense? So let's just do a review of Lewis structures in the form of compounds. Then we'll find those formula masses or molecular masses. And then we'll talk about using that information in terms of like entities, like that question of entities in dimensional analysis. Does that work for everybody? Okay, so let me first start. Let's say we have CCl4. Okay, so we have CCl4. What? Does anybody remember how to name that? It's carbon tetrachloride. Good. That's the name. Carbon tetrachloride. So carbon tetrachloride, C for carbon, Cl for chloride, and then 4 tells us that we have 4 of those chlorides. So we want to draw the Lewis structure. So how are we going to draw the Lewis structure for carbon tetrachloride? What can we start with? So we figure out our skeleton, right? And figure out what our central atom is. And you're saying that C goes in the middle. Why did C go into the middle of the atom? Because it's first. Most of the time, the first atom of the molecule goes into the middle, goes as the central atom. That's just a general rule. Most of the time, the first atom of the formula goes to the center of the Lewis structure. So it's going to be the central atom. Well, the other atoms are going to be your terminal atoms. Does that make sense to everybody? The only exception is hydrogen. Hydrogen will never be your central atom. And does anybody know why hydrogen wouldn't be a central atom?
Because it only holds so many atoms.
Yeah, and not just hold so many atoms, but like hold so many electrons, right? Or hold so many bonds, right? Hydrogen can only bond once. Doesn't make sense to put it in the middle and then you can't get enough bonds. Does that make sense? So hydrogen is never going to the middle. And if you see carbon, it's pretty safe to assume that carbon's going to go in the middle. Carbon is one of those that like can bond a lot. So it probably is going to go into the middle. Make sense? So we figure out what our central atom is, what our terminal atoms are. What would be the next step? What can we do? So what we can do is draw in 4 single bonds. Okay. So we draw in 4. So we found out our central atom, found our terminal atoms, and then drew single bonds in between the central and the terminal. What would be the next step? You have to count each atom's, what kind of electron? Valence, exactly. So the next thing we can do is we can count the number of valence electrons each atom has, right? So our valence electrons are for carbon and chlorine, right? So how many valence does carbon have? Has 6 valence, or does it have 6 total? Yep. So carbon has 4 valence. Does anybody know how to find that? Right? It's in group 14. Yeah, group 14. 14 minus 10 gives you 4 valence. Or you could just memorize from group 1, 1 valence, group 2, 2 valence, group 13, 3 valence, group 14, 4 valence. You could also do it that way. Either way works. So carbon in any group 14 non-metal is going to have 4 valence. Then, what about chlorine? Has 7 valence, right? And why does it have 7 valence? Because chlorine is in group 17, and group 17 non-metals have 7 valence electrons. Make sense? So far so good? So, but the thing is, are we done with counting our valence? No, why? Because chlorine is there 4 times, right? So you have to multiply that 7 by 4, which gives you 28, and then 4 plus 28 is 32. Right? And you have your calculator, so if you can't do that math in your head, which is perfectly okay, if you can't do that math in your head, you have your calculator available. So we have this, what does this 32 mean? How does that apply to our Lewis structure? Exactly, so this 32 valence electrons tells us that in this Lewis structure, you have to have 32 valence electrons on the structure. And that's as many as you can have. You can't go above, you can't go below, otherwise you didn't complete the Lewis structure. Does that make sense? And the way, what do you count to determine that you got 32 valence? What's involved in, is it just the pairs of electrons? Is it single bonds, double bonds, all of the above? All of the above, right? These single bonds represent valence electrons. Lone pairs drawn around terminal atoms or central atoms are part of the valence. Does that make sense? So right now we have 2, 4, 6, 8 valence that is already used up. Does that make sense? So we have 2, 4, 6, 8 valence electrons that are already used up. Because single bonds, how many electrons are in a single bond? 2. Every single bond represents 2 electrons. What if you had a double bond? How many electrons? 4. So if you see 2 bonds between 2 different atoms, then you have 4 electrons. How about a triple bond? 6 valence. Does that make sense? So far we have 8 valence, and that's going to give us 24 more electrons that we can use. Does that make sense? So, how do we go from here? What do we do? So you start doing the pairs on the terminal atoms, right? When you have extra pairs, that extra electrons, you start putting lone pairs on the terminal atoms first, and then you go to the central atom if needed. Make sense? So we do 2, 4, 6, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Is that complete? Do we have a total of 32 valence? We do. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Right? Good. And then does all of the atoms have a full valence? Yes. Carbon, does it have 8? Yes. Chlorine, does it have 8? Does that make sense? So, carbon, all of its valence are involved in bonds. So all 8 electrons of carbon are going to be found in their bonds to the terminal atoms. Does that make sense? While chlorine, 2 of its electrons are in bonds, while the other 6 are what's called lone pairs. These electrons belong only to chlorine and not to carbon at all, theoretically. Does that make sense? And again, this is a 2D structure of a 3D object. So this isn't a perfect replication of what's going on. We'll talk about, we might talk about geometry later on in the semester, but right now, this is just the best representation we can do in a kind of 2D way. Make sense? So is it clear how to do Lewis structures? Yes? So let's say we drew our Lewis structure, and Dr. Franco asks, what is the molecular mass? So how do we find the molecular mass of CCl4? What do we do here? Take the mass and exactly. So, because what is molecular formula mass? It's what? What's the definition again? Sorry, what is the definition of molecular formula mass again?
still the sum of the averages, or is that just one?
No, so it's the sum of the averages of atomic mass, right? And molecular mass is specific to covalent sum, right? But it's still the sum of the averages of the atomic masses. So to find the molecular mass, we have to take from the periodic table our atomic masses and add them all together, right? So carbon isn't it like 12.008 on your periodic table?
No, 12.
0.01, okay, because sometimes it's 0.008, sometimes it's 0.01, it changes. Okay, and then what about chlorine? 35.45. But is that all we add up? Because what do we have to do? Yep, so we have to multiply chlorine by how much? 4. Exactly. So we have 12.01 plus the 35.45 times 4, right? And that would be your molecular mass of carbon tetrachloride. Plus, not minus. So it should be 153.81. Is that what people got? That is math? Does that make sense on where we got all of that information? And again, you guys aren't expected to memorize your masses, right? Your atomic masses. You'll be given that information. You'll be given your periodic table. So, what is the unit of molecular mass? It's the AMUs, the atomic mass units. However, what happens is when we start doing dimensional analysis, what we're going to end up doing is that this AMU is super, super, super tiny. So we need to kind of expand it and make the units actually 153.81 grams per 1 mole. So you can see it written as this, or it can be written as this 53.81 grams per 1 mole. These two things are technically the same thing, but this is the more official one because that's the actual units found on the periodic table as AMUs, but this one is used when we do dimensional analysis. Does that make sense to everybody? Is everybody on the same page? If you have any questions, please stop me. I don't mind being interrupted for chemistry stuff. Okay? So if I need to repeat, if there's gaps, let me know. So, does that make sense? So, let's do the Lewis structure of ionic compounds instead. Because, again, what happens in covalent compounds? So in covalent compounds, you share electrons, right? So when we draw our Lewis structure, we draw in these bonds, right? We draw in single or double or triple bonds. In ionic compounds, what happens in ionic compounds? They transfer electrons, right? So ionic compounds transfer electrons. So are we really going to see bonds like we do in covalent? Not really, right? Not quite the same. So let's look at that. So let's say we have MgCl. So let's say we have MgCl2. What's the name of that? Yep, magnesium chloride. Magnesium Laura.
She doesn't get sent us our.
Yeah, because sometimes what she'll do on dimensional analysis questions is that she won't give you like the formula, instead she gives you the name. So like this, instead of giving you this, she give you this. And you're supposed to know, oh, well, magnesium chloride or magnesium phosphate is this formula. Does that make sense? So you still need to know your polyatomic ions because it might appear where she just gives you the name. Okay. So, what do we do here if we're drawing the Lewis structure? Right. Yeah, so you still have this kind of, still considering what goes in the middle, right? Even though you might not have bonds, you still have to consider what goes in the middle. So magnesium gets surrounded by your chlorine, your 2 chlorine, right? So what's next? Do we do exactly the same stuff as we do in drawing Lewis structures for covalent compounds? No. Because we don't really care having the right amount of valence within bonds, right? Because there is no bonds officially. So, anybody have another idea of what could be done?
Would you just take a photo of the valence electrons and apply that to the technology platform?
So, yeah, so you could still figure out the valence and then just apply them to your chlorine, right? Because the chlorines are going to end up being the ones with the valence, right? Magnesium is going to lose its valence and chlorines are going to gain, right? Because that's how ionic compounds work. Another way you could do it is you could draw out the valence for all of them. Like you can draw out 7 for chlorine and 2 for magnesium, and then just show and just move the electrons to where they're supposed to be from magnesium to chlorine. Does that make sense? So either way is correct. So you could do it like this. And then you can visually be like, oh, well, magnesium has 2 valence electrons. Chlorine, each chlorine has 7. If magnesium gives 1 to this chlorine and this chlorine, then everybody's happy. So you could visually do it like that. Does that make sense? What's confusing? So, because the bonds represent sharing electrons. So like, when you draw a bond between carbon and chlorine, this identifies that this carbon is sharing its electrons with this chlorine. Does that make sense? But is there sharing going on between magnesium and chlorine? Because what happens in ionic compounds with electrons? They take or exchange, right? One gives up its electrons to the other. Does that make sense? So magnesium, being the cation, gives up its electrons to the chlorine that is the anion. Does that make sense to everybody? So what ends up happening is, I have this.
Is it either electron or
Exactly, because if you remember, electronegativity kind of explains why this happens, right? Magnesium has a lot less electronegativity than chlorine, so chlorine's like, hey, give me your electrons. Does that make sense? And then this ends up, all of these being a lot more stable now than they were before. Does that make sense? So then you end up drawing brackets around them. And they're attracted to each other because of the charges.
Did you put the charges in the little brackets? Like just put chlorine and then put the charge in the little bracket?
Like this instead? Yes, you can do that too. So either way is fine, again. So you can do that as well, where the little brackets are around the chart instead. Does that make sense?
So that's like the final answer, that's how you rank up the test. Or like you just said.
Yeah, because what's happening is that they're attracted to each other because of their charge and not because they're sharing electrons. Does that make sense? So, and so that's kind of the final sort of thing. Does that make sense to everybody? So you could do it the way you suggested, where if this makes sense, you don't have to listen to the next part. But if you want to see it in a different way, what you could do is, because everybody's brain works differently, what you could do is still add up your valence, right? Magnesium has 2. Chlorine has 7, but times 2. So you get a total of 16, right? And the final product would end up being magnesium doesn't get any valence, right? Because magnesium loses valence as a cation. And all of the valence would just go around your chlorines. Does that make sense? Or you get you still get the same thing, it's just a different way to do it. If this makes sense to you, then do it this way. If drawing out what the valence looked like originally and then just exchanging them makes more sense, then do it that way. Does that make sense? It really depends on what is clear. Some people need it to be drawn out in the original format where magnesium had 2, chlorine has 7, and then you show the exchange. For some people, this works well too. So whatever works is fine, as long as you get the right answer. Okay? Does that make sense to everybody? Okay, so that's how you draw out the low structure for an ionic compound. You wouldn't have bonds per se. It's still a bond, but you just don't have the line because there isn't sharing of electrons. Makes sense? So what would be the formula mass? Not formula mole, formula mass of magnesium chloride. How would we find this? You would have done the same thing as you would have carbon tetrachloride, right? You'd find the average, you would sum up the average atomic masses from the periodic table. How much does magnesium weigh? 24.31? Yeah. Okay, and then chlorine is 35.45. But there's 2 of them, so we multiply it by 2, right? And then we get 24.31 plus 104.3. You get 95.21 AMU, or it would be 95.21 grams per 1 mole. Does that make sense? And remember formula mass, Dr. Franco seems to want you to think that Dr. Franco wants you to associate formula mass with ionic compounds. Makes sense? So far, so good? Okay, so let's look at magnesium chloride for a second. And look at it in terms of entities. So let's look at magnesium chloride. So think, especially in the next coming weeks, it's really helpful to think of chemistry as kind of like baking or cooking, right? You have a certain amount of this reacts with a certain amount of this to form something else, something new, right? So we're gonna be doing reactions. We're gonna be balancing reactions and looking at those things and understanding, in a sense, recipes that allows us to form new products, new material. So starting off and talking about like entities helps you get into the mindset of when we have magnesium chloride, we have 1 part magnesium, 2 parts chlorine. And that's what magnesium chloride is. If you go back, do you guys remember in the first chapter, she talked about the rule of definite proportions, right? In order to be a certain compound or a certain molecule, you have to have a certain amount of whatever element we're looking at, right? H2O and H2O2, 2 different things. Their proportions are different, right? So magnesium chloride, in its law of definite proportions, is 1 magnesium to 2 parts chlorine. Those are the entities that make up magnesium chloride. Does that make sense? And those parts that we talk about are moles. Did she mention that term? Did she start on that term? So moles is the way we say entities, or one thing we call entities in chemistry. Moles is a way to describe that we have 1 part magnesium, 2 parts chlorine. So in other words, we have 1 mole of magnesium to 2 moles of chlorine in magnesium chloride. Does that make sense? So it can get a little more confusing because it's like, so in when we bake, we say that we have like 1 cup of flour, right? But then we don't say for every 1 cup of flour, we also have 4 cups of flour too. Like when we talk about cups of flour to go into like tablespoons, we use distinct entity names for separate things, right, when we're baking. Chemistry doesn't really do that. What ends up happening in situations, which can be really confusing for some people, which is understandable, it can be confusing. When I say I have 2 moles of magnesium chloride, the thing is, I can still describe how many parts of magnesium and chlorine I have of magnesium chloride. So for every 2 moles of magnesium chloride, I end up having 2 moles of magnesium and 4 moles of chlorine. Because when we bake, we would use different terms, right? Instead of using cup for every single proportion size, we would use cup, tablespoon, teaspoon. But in chemistry, moles is kind of the universal term for each proportion size, in a way. Does that make sense? Except for when we get to like molecules and atom sizes. So moles is just a substitution in a way for the word entity. Make sense? So that's an important thing to remember when we start doing dimensional analysis and when we start doing balancing reactions. Understanding this breakdown is going to be important.
So she gave you that you have 2 moles of magnesium chloride. Would you start by converting that to
So what could happen like on the quiz or the test? What she could do is she can say like, you have 2 moles of magnesium chloride, how many moles of magnesium do you have in those 2 moles of magnesium chloride? What you end up doing is you multiply the amount of moles of the whole thing by the subscripts. Does that make sense? So that's how I got 2 moles of magnesium and 4 moles of chlorine. And then for dimensional analysis, what she could do is how many grams of magnesium chloride do I have?
Well, she said last night that she could start with the grams, or she could start with the
So one example of this is if she gives you the moles, she could ask you how many grams of magnesium chloride, or how many grams of just magnesium you have.
Did you do that by finding the molecular formula mass?
Exactly, so the question would be, you have 2 moles of magnesium chloride, how many grams of magnesium chloride do you have? Your first step from going moles to grams would be finding your molecular mass or your formula mass. Well, actually, it wouldn't be molecular mass, it would just be formula mass, sorry. The first thing you would do is find your formula mass of magnesium chloride. Does that make sense? No. So let's look at that. So we're going from moles, and then we want to go to grams, right? That's what this question is telling us. We're given moles, we want to go to grams. So do you remember when we did the formula mass for magnesium? For magnesium chloride, it was magnesium was 21.31? 24, okay. And then chlorine was 35.45 times 2, and we got 95 point something. What was it? 95.21, right? And we said it was AMUs. What's the other unit we could use? Or it could be 95.21 grams per 1 mole. This is 2 different units that can be used for the formula mass of ionic compounds or molecular compounds, right? So this, you remember how we did conversions and dimensional analysis a couple weeks ago or a couple months ago? You remember how we used conversions, conversion factors, conversion units? This is our conversion now. This formula mass is going to be our conversion for a question like this. We can go from moles to grams using this grams per 1 mole unit. Does that make sense? So the thing is, the way we set this up would be 2 moles of magnesium chloride times 1 mole over, sorry. I I got too excited. Be 95.21 grams of magnesium chloride over 1 mole of magnesium chloride. We're using our formula mass as our conversion factor to go from moles to grams. Does that make sense now? The mole units would get canceled out, and then we're just left with the unit of grams. And then we do our calculation where we do 2 times 95.21 to get our grams of magnesium chloride. Which we should have gotten, right, is 90.42 grams of magnesium chloride. Right? Does that make sense to everybody? So that's the nice thing about this conversion. Anytime you go from moles to grams of a compound or a molecule, you're going to use the molecular mass. Or if you go from grams to moles, you use the molecular mass. You just flip it upside down.
How is it that you got 190?
So what we did was we multiplied the 2 times the 95.21, and since it's divided by 1, it's end up being the same. So it would be
So, numerals don't cancel out, so.
just the units. Exactly. It's just the units that cancel out, not the number. The number is still there. Okay? Does that make sense?
Yeah.
Yeah. So the number stays. It's just the units that cancel out. Does that make sense to everybody? So is that a little bit clearer about what she was doing in class and where that was, how that was happening? So is there any questions about that? Or is there any questions about anything else? Okay, so molar mass is more specifically this, like using grams per mole is called molar mass because it's the mole, it's mass per mole. Does that make sense? So when your unit isn't AMU but instead grams per mole, that's the molar mass. Make sense? So it's just like making it even more specific. And the molar mass is what we use to do conversions because AMUs, they're good to tell you how much that compound weighs, but we can't do much math with it because we don't measure things in AMUs and all that. Makes sense? So we kind of have to scale it up into molar mass. Is there any other questions you guys have?
When it comes to electron configuration, how do you determine those with ion bonds?
So, electron configuration, so like electron configuration, if you have a positive charge, then you're going to have 1 less. Or no, if you have a positive charge, you have less electrons. So if it's a +1, you have 1 less. If +2, you have 2 less. Does that make sense?
Yeah.
And then like if you have a negative charge, then you're gonna have more electrons than expected. So, for example, like sodium as an ion, it has a +1 charge. How many electrons does sodium usually have? How many electrons? 1. 11, just total electrons is 11, right? So sodium has 11 electrons, but as sodium at plus, as an ion, it would only have 10 electrons. So you do the electron configuration based on those 10 instead. Does that make sense? So, do you need that demonstrated or is that clear?
It's clear there, but say we had to predict like an electron configuration.
Mhm.
So, aluminum 3+,
Mm-hmm.
she has here that omitted certain portions of the configuration. I don't understand where this is for that.
So, like aluminum is aluminum. How many electrons does aluminum have as an element with no charge? How do we find out how many electrons an atom has?
Their atomic number on some aspect.
Alright, so their atomic number is equal to protons, which when it's neutral is equal to electrons, right? So the proton number for aluminum is what? 13. So that means we have 13 electrons when it's not charged, right? So it would be 1s2, 2s2, 2p6, that's 10, 3s2, 3p, that's, right? 2 plus 2 plus 6 is 10, plus 2 is 3, 12, brain part, I'm sorry. So the total is 13, right? So as a 3 cross charge, aluminum, what does that mean for its electrons? Okay. It's going to take away 3, right? And what kind of electrons gets taken away when you form an ion? Is it core electrons or valence electrons? It'd be valence, right? And what are our valence electrons in this example, in this first one? Where are our valence electrons found? These are our valence electrons, right? Because these are the electrons found in the outermost shell. They're found in the third shell, which is the furthest out in this electron configuration. Does that make sense? So it would be these 3 that are taken away to form this ion. So what you end up having is 1s2, 2s2, 2p6 as the electron configuration of aluminum 3+. Does that make sense? Does everybody? I know that's it's a good review because then your questions on your test are going to be asked about that, right? So you guys are having a test on the 25th of March, 23rd, okay, or your 25th, 23rd, okay. And I will be looking into doing a review session before the test, so that way, which might be. Yeah, so I'll look into doing a review session before the test, before both tests, making sure that everybody, probably on that Monday night, because nobody's going to be here on that Sunday, probably. Most people are going to be like, I'm going to wait until Sunday night to get here, and most people can't. Anyway. But does that make sense now? Okay. So remember, with electron configuration, when you form an ion, the ion is going to get either added or the electrons are going to get either added or removed to the valence. Okay? To the valence electrons, which are found in the outermost shell. Make sense? And don't forget the videos that I post online. And I usually put it in case you don't you don't know, there's the videos that I post online, and in the summary, I say what we read over. So if you have specific questions, there are videos about valence electrons. There's videos, and then last video, we talked a lot about doing the Lewis structure and drawing out the Lewis structure. So in case today wasn't enough, there's more on Blackboard underneath the SI and LA for chemistry students. Okay?
Are you gonna post
I'll do a lot of posting over spring break. I apologize that I've fallen behind. I know I've been a bit of a slacker. It's just grad school applications and grad school interviews, and it just, yeah, and then tests and my own stuff. But I will be getting back onto material and posting stuff. I'm all day off on Saturday, which I plan to sleep, do work for Chemistry 101, and get ahead from my classes. So those are what I'm gonna do. You guys are number 2 after sleep. Okay. Oh yeah, of course. I'm gonna be eating the whole time except for the sleeping part because I eat constantly. But you guys are number 2 other than sleep and eat. Sound good? Okay. So we have a session tomorrow. I know a lot of you can't make it tomorrow or you're gonna be leaving town. That's totally fine because I would leave when I can. And